Consider the relationship between a straight line and a circle. In this configuration, there are no points of intersection between the straight line and the circle. If we move the line to a different position, we may have somewhere where the line and the circle intersect in two distinct points. And then we may have a third situation where the straight line and the circle just touch where there is one point of intersection. We say in this case that the straight line is a tangent to the circle. How can we investigate these cases? In this example, we're asked to find the coordinates of the points of intersection of the straight line x plus 2y subtract 3 is 0, with the circle x subtract 4 squared plus y plus 3 squared is 5 squared. Graphically, we have this situation, and we are trying to find the coordinates of the points of intersection. Well, what we have here are simultaneous equations, and this is best solved by substitution. So let's take the equation of the straight line. X plus 2y subtract 3 is 0. We will have to rearrange this into the form either x equals or y equals. In this case, it's going to be more convenient to rearrange that so that we have x is equal to 3 subtract 2y. Why did we choose this form instead of y equals? Well, this way round we don't have any fractions. Dealing with fractions is awkward, always best avoided if possible. Now we can substitute this expression for x into the circle equation. So instead of x subtract 4, we have 3 subtract 2y subtract 4 squared plus y plus 3 squared is 5 squared. We may as well already simplify that to 25. Let's just clarify what that first bracket becomes. 3 subtract 2y subtract 4, we have negative 2y subtract 1 squared plus y plus 3 squared is 25. Just before we expand the brackets, let's make the observation that if you square a positive or negative value of the same magnitude, you will get the same answer. For example, 3 squared and negative 3 squared come to the same thing. What we can do with this first bracket is realize that if we had positive 2y and a positive 1, then when we square that, we will get the same answer as if we square negative 2y subtract 1. And writing it like that would just make life easier for us. This was not an essential step. We could have expanded the bracket as it already was, but this will make our life easier. Let's now do that expansion. Expanding the first bracket, we'll have 4y squared plus 4y plus 1. Expanding the second bracket, we will have y squared plus 6y plus 9. That's still equal to 25. So, gathering terms, we will have 5 y squareds and 10y subtract 15 is 0. And before we try and solve that, it will be convenient to divide through by 5, giving us y squared plus 2y subtract 3 is 0. That is going to factorize. We will have a y at the beginning of both brackets, and a moment's thought helps us to see that that will be y plus 3, y subtract 1. So we either have a y value of negative 3, or we have a y value of positive 1. Using our rearranged straight line equation, we can see that the x which goes with negative 3 is 3 subtract 2 lots of negative 3. 3 subtract negative 6, 3 plus 6, that's an x of 9. Here we will have 3 subtract 2 lots of 1, 3 subtract 2, we will have an x of 1. So the coordinates of the points of intersection of the straight line and the circle are negative 3, 9 and 1, 1. Going back to our diagram, we deliberately concealed the axes so that this wasn't obvious from the beginning. Bringing the axes back, we can now see that we have the correct points of intersection. The next question asks us to show that the straight line 4x plus y plus 5 equals 0 does not intersect the circle x plus 5 squared plus y squared equals 12. Here's a graphical representation of that situation. We can see that there's not a lot in it. The line nearly touches the circle, but not quite. But how can we prove that they do not intersect? Once again, we have simultaneous equations. Let us for the moment not prejudge the fact that there aren't going to be any points of intersection. Let's see what happens if we do try to solve them simultaneously. Taking the straight line equation, we can rewrite this as a y equals quite easily. So that rearranges to give us that y is negative 4x subtract 5. Now let's try substituting that into the equation of the circle. We will have x plus 5 squared plus negative 4x subtract 5 squared is equal to 12. Before we go ahead and try and solve this, we'll use the same observation we used in the last example, that if we square positive 4x plus 5, we will get the same answer as if we square negative 4x subtract 5. So let's expand the brackets. We will have x squared plus 10x plus 25 for the first bracket. We will have 16x squared plus 40x plus 25 from the second bracket. All of that is equal to 12. Collecting terms together, we have 17x squareds plus 50 x's plus 38 is equal to 0. In other words, we have a quadratic equation which will give us the values of x where the line and the circle intersect. But we have a method to discover how many solutions a quadratic equation has. We can check its discriminant. In this case, the discriminant is 50 squared, subtract 4, lots of 17, times 38, which is negative 84, which is less than 0. Therefore, we can say that the quadratic has no solutions. And if this is a quadratic which is giving us the x-coordinates of the point of intersection, we can therefore say that there are no points of intersection. We therefore know that the straight line and the circle do not intersect. This question asks us to describe the relationship between the straight line 2x subtract y plus 1 is 0 and the circle x subtract 3 squared plus y subtract 2 squared is 5. When we are asked to describe the relationship between a circle and a straight line, we are really being asked, how do these intersect with each other? Twice, once, not at all. So, rearranging the straight line, we have that y is 2x plus 1. Substituting into the circle, we have that x subtract 3 squared plus, now instead of y we can write 2x plus 1, subtract 2 squared is 5. Simplifying that second bracket, we'll have x subtract 3 squared plus 2x subtract 1 squared is 5. Expanding the brackets, we have x squared subtract 6x plus 9 from the first bracket, and 4x squared subtract 4x plus 1 from the second bracket is equal to 5. Combining terms, we have 5x squareds subtract 10x plus 5 is 0, and it will be easier to deal with this if we divide through by 5, giving us x squared subtract 2x plus 1 is 0. Now let's check the discriminant of that quadratic. Its discriminant is negative 2 squared subtract 4 times 1 times 1, which is 4 subtract 4, which is 0. Therefore the quadratic has one solution. There is only one x-coordinate where the line intersects the circle. We have to be slightly careful here, because it would be possible for a straight line to intersect a circle twice, even though there is only one x-coordinate. Here is an illustration of that happening with the circle in this question. The straight line x equals 4 intersects a circle twice, but both of those points have the same x-coordinate. However, that is only going to happen if we have a vertical line, and it is easy to see from the equation of the straight line in this question that it is not a vertical line. In fact, it looks like this. So we can conclude in this question that the line is a tangent to the circle. In this question we are told that the line y equals x plus k intersects a given circle at 2 points, and we have to find the set of possible values of the constant k. Here is a way we can visualize this. The straight line has a given gradient, but different values of k will give us different y-intercepts. So we can see that there are some possible y-intercepts for which that line cuts through the circle twice. But how can we find them? Well, again, we have simultaneous equations. Let us substitute this straight line expression for y into the circle. That will give us x plus 7 squared plus, and instead of y we can write x plus k plus 3 squared is 6 squared. Before we do the expansions, I think it will help us to write that second bracket as x plus a number, that number being k plus 3. Then we have to square that. So expanding the brackets, we have x squared plus 14x plus 49 for the first bracket, and we have x squared plus 2 lots of k plus 3 x's, and we also have k plus 3 squared. All of that is equal to 36. We have a little bit more expanding to do before we can collect everything. X squared plus 14x plus 49 plus x squared. Now let's expand this. We will have 2kx's and 6x's. Expanding this bracket, we will have k squared plus 6k plus 9. All of that is equal to 36. Now, collecting together, we have 2 x squareds. How many x's do we have altogether? Well, let's be careful here. There are 14 of them from this term. There are 2k of them from the next term with x's. There are 6 of them from the term after that. Those are all of the x terms. And how many constants do we have? 49 and k squared and 6k and 9, and if we subtract the 36 from the other side, there we go. Right, so let's simplify that just a little bit more. 2x squareds. How many x's? 2k plus 20. What's the constant on the end? K squared plus 6k plus 22. Now we know that the line and the circle intersect at 2 points. So this quadratic equation that gives us the x-coordinates of those 2 points is going to have 2 solutions. And if it has 2 solutions, then its discriminant is going to be greater than 0. So this implies that that discriminant, which is b squared, now b is the number of x's, so that's 2k plus 20 squared, subtract 4 times a, which is 2, times c, which is k squared plus 6k plus 22, is greater than 0. We have quite a bit of tidying up to do here. Let's expand that first bracket to give us 4k squared plus 80k plus 400. Let's expand the second bracket to give us negative 8k squared subtract 48k, subtract 176, that has to be greater than 0. Let's collect terms together. We have negative 4k squareds plus 32k's plus 224. That has to be greater than 0. Before we go any further, let's divide through by negative 4, giving us k squared, subtract 8k, subtract 56, and don't forget, when we have an inequality that we divide by a negative number, we have to reverse the direction of the inequality, so that is less than 0. Now we know how to solve a quadratic inequality. We first have to replace the inequality with an equality to try and find the critical values. In this case, unfortunately, that's not going to factorize. Let's do this by completing the square. So we'll have k subtract 4 squared, subtract negative 4 squared, subtract 56 is 0. That gives us that k subtract 4 squared, well, negative 4 squared is 16. Negative 16 and negative 56 is negative 72, but if we add that to both sides, we'll have a 72 here. Taking the root of both sides, we'll have that k subtract 4 is root 72, which is 6 root 2, but plus or minus. So the critical values are that k is 4 plus or minus 6 root 2. If we were to draw a little sketch of this quadratic, we would therefore know that it cuts the k-axis at 2 points that we've just worked out, and we would also know it has this shape. We want the values where this is less than 0, below the axis, that will be in between these critical values. So therefore the set of values for k for which that straight line intersects a circle at 2 distinct values are values of k in between 4 subtract 6 root 2 and 4 plus 6 root 2. So quite a long and involved example which covers several different techniques, but a good example of a comprehensive and potentially high-scoring question.